Hello, this is the second part of robust design, second video of robust design. So we'll go to the slides, and what we discussed in last video is I took you through the three quality control philosophy that recommended by Takuchi-san. So what I'm going to do in this video is we're going to go through the slide of robust design. Okay, let me turn off the camera, which makes me feel more comfortable. This is the slides of a robust design, chapter number 8. Okay, so the first few slides I will take you through really quickly. We'll go through really quickly because fundamentally we have discussed all this in the previous video. So where we are now, I'm not going to talk about the story of the auntie, but we have done process capability, and now we are reaching the top hierarchy of quality control improvement methodology hierarchy, DFM, which stands for Design for Manufacturing. You should understand what is DFM, because we have discussed this in last video. Okay. And yeah, in fact, process control, I can't exactly put as green at this moment, because as you might aware, I have changed the syllabus slightly. Process control, SPC, we should discuss variable control chart and attribute control chart. But so far, we have yet to discuss attribute control chart. The reason that I pushed the chapter of attribute control chart toward the end of semester is because you have to know machines of process capability and DFM in order for you to complete your project task 2 and 3. So we're talking about DFM today, design for manufacturing, or so-called robust design. So this is the history of Taguchi. By now you should know me well, or you should know me, maybe not well. You should know me that I don't like to read through the slide, I think. And these are the fundamental information that you can read and you can understand by your own. Takuchi-san is an engineer, he's an electrical engineer, okay? He's one of the guru of, great guru of qualities. This is some of the history of Takuchi's work in a R&D company before. Okay, you can read through. All right, so yeah, perhaps this is something that we can sort of discuss a little bit. You remember in last videos, we did discuss the first quality control philosophy for Takuchi-san is Takuchi-san is not the son of Takuchi. When we say Takuchi-san, in Japanese, san means Mr., right? So it's Mr. Takuchi. So the first philosophy of quality control recommended by Takuchi is with the name of quality control. Remember, if not remember, you have to watch, rewatch. You have to watch back the first video. Quality control based on Takuchi can split into two. One is called online, another one is offline. So online, I sort of like indicated in the last video, I said inline is approximately equivalent to detection approach, and offline is sort of like quite similar to a prevention approach. Therefore, there are some scholars argue that the idea that proposed by Takuchi is nothing new. It's not developed by Takuchi, but we don't want to argue this in this module. In this module, we purely sort of like try to apply the philosophy that proposed by Takuchi in statistical quality control. Okay, so the history part of Takuchi, let you go through by own. Then these are the three philosophy of Takuchi that we discussed in last video, which is also going to take you through very quickly. The first philosophy of Takuchi is saying that quality should be designed into the product, not expected into it. By now, you should understand these statements because we take quite a long period of time, long duration to discuss this in the last video. That's the reason that I don't want to start the slide immediately. If I showing the slide to you and saying that quality should be designed into product, I don't think you can understand. But by now, if you really watch the previous video carefully, pay attention when watching the video, then you should be able to understand the first point. And the second point, quality is best achieved by minimize the variation or the deviations from a target. This is the second philosophy that we discussed in last video. And the third point is talk about cost of quality. We also discussed quite detailed in last video, something related to Takuchi quality loss functions. Okay. And this is the detail of the first concept of first philosophy of Takuchi. Takuchi addressed quality in two main areas, offline and online. Okay, so online is sort of like the SPC and sampling that we have learned so far. And offline is saying that quality can be improved to product or process developments. Okay, so this is sort of like recap from what we discussed last week, not last week, last video. And what is this slide talking about? The better improve quality is to, so from offline and online, Takuchi philosophy suggested that offline is better than online. So quality should be designed into the product, not inspected into the product. So offline is the strategy that proposed by Takuchi-san, and it's quite similar to the prevention concept that we discussed in chapter 1. And if we say that we need to design quality to product, offline means design quality to product. So how is we have to design until the design is robust enough? That's how we call robust. And robust, I mean robust, as explained in the last video, is immune to the influence of uncontrolled environment factor. Also explained in last week. Okay, not last week, quite last video. And the second concept is talking about variation. Then I also mentioned in last video that one of the important thing is one of the important philosophy that recommended by Takuchi was design for manufacturing. And the process of design for manufacturing is you need to study the variation of the process and then develop the parameter of the product and process. And the third is talking about the quality, cost of the quality or cost of the product that based on the Takuchi quality loss functions. So for these three philosophies, what we start and in this video until now, basically recap what we discussed last video. And what we summarize for last video, we're saying that based on these three philosophies, robust design make up of three steps. Number one is called system design. Number two is called parameter design. And number three is called tolerance design. These are the ones that we concluded in last video. Okay. And this is the Takuchi quality loss function. I want to discuss further. So to achieve robust design, there are three steps that proposed by Dr. Takuchi. Okay. System design, parameter design, and tolerance design. So, okay. These are something new that we did not discuss from last video. We did not discuss in last video, and it's a continuation for last video. What is system design? System design is okay, to determine the suitable working level of design factors, okay, including design testing system based on design selection material. Okay, so we use an example. What system design for your example? Okay, to make your life easier, we take example of your project. Park a car into a parking lot. So what is the system? The system is the size of the parking lot. Okay, the type of the car that you use, which driver you choose. This is design the system. Why is it system? A parking process system. You might feel, okay, if I say park your car into a parking lot, normally because you are familiar with the parking process, so what you will do is you will start your engine, drive the car, park into the parking lot, and this is a system. And this system of parking a car in the parking lot involves the car types, the drivers, the gate size. But in subsequent example, I'm going to show you how system design is applied in the actual design. Yeah? So at this moment, this is system design. Okay. Then the second step is define the parameter. If I say that the system is the system that required to carry out the parking process is I need to have the parking lot. Therefore, the parking lot size is important. The system of parking a car into a parking lot require a car. So I need to select a car. So it's a system, right? So a system of parking a car into a parking lot, I need a driver. So that I need to select a driver. So I selected that. But coming to the detail example, what are the parameters that I should control on the system that's selected? Example, I selected a Vios, I selected a driver, Mr. A. So during the parking process, the one that can control is, in this slide, I'm saying that, example, the height of the driver's seat, you can adjust the height. And maybe this height is going to have influence on how well you park your car into the parking lot. Or the angle of the side mirror, okay, the speed that you drive to park your car in the parking lot. So these are the parameters. So to recap, are you able to differentiate between system and parameter? Again, system for me, I would say that is something that require for you to carry out the process. So that including the material, the parts. Huh? Okay, so based on current technology, in your case, it's based on your current process of parking. So in order to carry out the parking process, the system requires a parking lot. So we need to have the lot side or gate side. The system requires a car. Even without a gate or without a car, without a driver, the process cannot be carried out. So that is system design. Yeah? Then pattern design, I have the car, I have the driver. So how fast the driver is going to drive, that's a parameter. And then the height of the car seat, the angle of the side mirror, that is a parameter design. So again, parameter design, the parameter that's selected can be made up of controllable parameter and uncontrollable parameter. So we're only interested on controllable parameter. We are not going to control like the temperature of the environment temperature. Sometimes it's possible that the weather have impacts on the parking positions, raining day or sunny day. But we're not able to control, therefore that is uncontrollable factor. We're only interested in the controllable factors, okay? Before I proceed, bear in mind, because we're discussing the top level, the quality control hierarchy, as compared to process capability, SPC, and sampling, this is relatively more difficult to understand, so you must bear in mind. Okay, so right, maybe I use another example. When I send the Google form to ask from what to collect the feedbacks on this online teachings, approximately, maybe around 97% prefer pre-recorded video. But there are few of them, maybe one or two, propose me to give more example. Although why using the parking example, I think it's a good example. More example, okay, example. I want to design, we don't talk about product. Product may be difficult for you to understand. We're talking about a cup of coffee. I want you to make a cup of coffee for me. What is the system? The system could be a coffee maker. You could make a cup of coffee for me manually. Boil the water, add the powder, add the sugar, add the milk. And correct, don't forget to add the water. And then there are two systems. Which system are you going to choose? Or your system, perhaps you just use a grapefruit, order a cup of coffee for me. If that is the case, then no need to do a robust design. Okay, there are three scenarios as well. I want my product is I want a cup of coffee. Then you're going to prepare for me, and I want to make sure that you're going to apply robust design in making a cup of coffee. The first method, you're going to use a coffee maker. Second, you're going to make a cup of coffee for me manually. Third, you're going to use grapefruit. The third is not in our consideration because you're not going to design the cup of coffee for me, just order for me. So in the first two scenarios, coffee maker, or make it manually. These are the system. Example, I choose the second system, make a cup of coffee manually. So the design factor here that involve, number one, I need to have the powder, correct? I need to have a cup, okay? So that are the system that requires. So we come to parameter design. What are they? I have the blank water. I need to have water. Like I need to have water. I need to have sugar. I need to have milk. I need to have a cup. Okay, that is the fact. They call it factor. They are the elements that need into the system. Okay, you make a cup of coffee using manual method. So the system requires cups, a glass or cup, a kettle to boil the water. You need to have a blank water. You need to have a sugar. You need to have coffee powder. I need to have milk. Okay, so that is the system. Parameter means, okay, I have the sugar, I have the powder, coffee powder, I have the water, I have the milk. How many spoons of powder that you should add into a cup of coffee? How many spoons of milk, how many spoons of sugar, and the amount of water? That is parameter. That's parameter. Okay, and then besides that, they also have other parameters have impact on the taste of the coffee, how good the coffee is. This example, the temperature of the cup. What else? Okay, the temperature of cup example. But that temperature of cup is something that's quite difficult to control. So this temperature of the cup that I'm going to use, I will consider uncontrolled factor. I'm not going to control. The factor that I'm going to control is how many spoons of sugar, how many spoons of milk, how many spoons of coffee powder, and the amount of water. Okay, so I need to set a level. This is called parameter design. Parameter design is how many spoons of powder, how many spoons of sugar, how many spoons of milk. And I keep repeating until I'm so tired. And the amount of water. Okay. And okay, optimum, what's the optimum condition, you see? In the paper that you're going to read, or maybe you have read, that I written there, there's one term we call DOE, dissolved experiment. I didn't use my pen today. DOE. Anyone have read the great article that I written. So design experiment. What design experiment? You see, if you make the first cup of coffee and you serve the coffee to me, I drink, I say, oh, it's too sweet. What are you going to do next? There are a couple of ways you can do. It's too sweet, you can reduce the sugar. But once you reduce the sugar, I say, okay, it's not so sweet, but it's too thick. Why too thick? Because once your sugar is reduced, perhaps the taste of the coffee become, it's a bit thicker, we say, right? Okay, a bit thicker. So this parameter, there's a so-called interaction. If I reduce, if too sweet, there are a couple of things I can do. I can add more water. I can add in more coffee powder, right? That will make not so sweet. Or I can reduce the milk, I can reduce the sugar. So in the design, in the robust design, in order for us to find the best match of the parameter, how many spoon of, I keep on repeating this, how many spoon of sugar, how many spoon of water, no, not how many spoon of water, how many spoon of sugar, how many spoon of milk, how many spoon of coffee powder, and number of water. In order to define this, we need to go through a process we call design experiment. This design experiment is going to so like give us optimum setting of the parameter, say that, oh, you put this amount of powder, this amount of sugar, this amount of milk, and this amount of water, then the cup of coffee will be the best in the world. Okay, this is called DOE in my article. I did explain in detail. Okay, and then the third is called tolerance. In life, if I say I want you to put 3 grams of sugar into a cup of coffee for me. As what Chia did, drawing a circle in whiteboard. He can't draw it properly, right? Some of the circle become triangle, some become rectangle, or some even become a love shape. So what is the story? What's the moral story? Is 3 grams of sugar put into a cup. It's quite impossible that every time you will put exactly 3 grams. Therefore, you need to have tolerance. Plus minus 3 grams plus minus 0.5. So the last step of the robust design is tolerance. So this is the one that the three concepts. The three concepts. Okay, let us take a look on my paper before I look at the actual example. Okay, this is a paper that I written many years back. When was it? 2014. All right, 4 of us from UTM, but only me that's still here. Retire, resign. Only me are still here. So this is talking about a robust design in one of the companies. In one of the, it's an actual case study of robust design. So what is this talking about? This is talking about, do I have the picture here? Let me take a look. If not, I will show you the slide. Okay, here. It's something that with the name of, I think, let me open the slide because, but before I show you the slide, there's one thing very important. Please, everyone of you, please keep this video to your own. Don't share with anyone because the slide they're going to show you next is a slide that I took from my ex-company. Therefore, please, if you share with someone else, maybe it will get me in trouble. So don't share with anyone. Okay, let me open the next slide, which is also not e-learning. Okay, this is a slide they're referring to. It's a training slide on robust design. Robust design. I will not take you through in detail because this is exactly what we learned. But what you can see from here is what we learned in our module. It's something that very practical. We're not sort of talking a story or making a story of a quality control methodology and then that's it for examinations. You don't have an exam. It's not okay. what we learn today is exactly what have been practicing in the industry for quality control. You see, this is exactly what you're learning today. Like you're learning, okay, SCP, CPK, blah, blah, blah. I will take you through. But this one, perhaps, yes, something that I want to share with you. Oh, this one, let me do this. If you remember the chapter that we discussed in process capability, I was telling you that in our module, we are targeted for CP2 for Six Sigma and CPK 1.5. That is a industry standard level. Some of the company, like my ex-company, at the time that I was there, which is how many years back? Oh, 6, 7 years back. At the time, the targeted CP is 4.0. All right, it's 4.0. You remember in the video talk about CPK, I said I'm not going to quote any number, but in the module we use 2 because different company might use different CP or CPK. 2 CP is great, no? CP 4.0 is great. CP2 means 3.4 parts rejected out 1 million. CP4 means 0 defects. Okay, don't show too long. This, okay, but I should show you this also later on. Now you see, SPC. This is a real SPC, you know. We learn something and then you use Minitab. But in real life, you see, the industry are not using Minitab because this is plot operator. This is actual SPC. So don't think that what you learn is for fun or is for exam. No? What you learn basically is exactly happening in the company. CTP, CPK, blah, 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 blah. Okay. All right. So robust design. Robust design in my ex company, we call it tolerance stack. Okay, tolerance stack. So we talk about system design, we talk about parameter design, and we're talking about tolerance design. What does it mean? You see, I give you another example. Since the comment said I didn't give enough example, which is I think I gave a lot. But it's okay. Anyone, whoever commented, don't feel bad. That's my style. Okay, so identify part must be okay. So these are the example of something we call a host and a one. So this is a host, and this is a one. Okay. So assume that you are a designer that assign a task to design a host and a one. So this one is going to fit into the host. So system design. What is system design? In this case, the system design. What is the system? The system is the one is going to insert into this host. Okay. Therefore, the system design for here is you need to identify what is the force that require or acceptable force that can insert and take up the one to the host and from the host easily. What are the force that require? Okay, so because this is a system, okay, we stop here short while. Then we back to the back to my paper. Okay, so in my paper, I did, you can read through here, what's process variation, what's the design limits, and then what's robust design, system design, what's system design? From product design point of view, system design refer to, denotes to selection of design parameter, correct? And based on product functional requirement. So this is refer to product operations, okay. So this is example, okay, I want to show example. Example of system design is in the host in the one example is a force that require to, oh no, this is another example. The force that require to activate on-off button by adapt for figure. This is a system design. Okay, and parameter design. Parameter design is a step used to identify critical design parameter, example, with significant influence on functional requirements, same as the coffee. Like the critical design parameter that has significant influence on the taste of my cup of coffee is the powder, the powder, the milk, and the amount of water. But the combinations, how many spoons of each of the ingredient, I need to find out using design experiment. Okay. And then subsequently, I need to define a tolerance. Why I need to define a tolerance? I need to define a tolerance until the design is robust. Then how to design? What is robust? Robust is when you park your car at midnight, heavy rain, current breakdown, you cross your eye, you still can park perfectly. So therefore, you need to define a tolerance that, which is the process can manufacturing the products and insensitive to the uncontrollable factor. Okay, so this is system parameter and tolerant design. So, and this is the process that we go through. Like, you can read through. Okay, then I'm going to take you through that how this process is carried out by using the slide. Okay, by using this slide. Bear in mind that this slide is slightly typical. You might have difficulty to understand this slide, so it takes time for you to understand. Okay, so the system is to insert a one into the host. Okay, so in order for me to do that, so I need to sort of like identify what is important for the system. Right? A system, in my previous example, is make a cup of coffee. What's important is when the coffee, I try it, then I must be satisfied. That is the important thing for the coffee example, cup of coffee. Example for making a cup of coffee. So in this example, the system is inserting the one into the host. So the important thing for this system is the force required to insert and the force required to insert. Therefore, in system design, perhaps some of the technical terms you don't understand. And the system design, the first thing that we need to do is we need to find what is the force required to insert the one and the nozzle. The one and nozzle, they call the hose, and this called insert the one into nozzle perfectly. So back to the paper, what I mean by the system design is here is to define a functional limit. Functional limit is a window opportunity for the product design is acceptable by user. If I design something that's too hard to insert or too loose, customer will not accept. Therefore, the first thing for the system design is I need to do a study, make a prototype, try what the force that would be acceptable by the customer. So I did a study and then concluded that assembly force will be from 3 to 5 Newton between component A and B. Quite A and B easy. So this is system design. Okay, system design. Example, in this example, the system is to insert component A to B and take it out. Okay, so the process assembly component A and B, the system itself, the important thing is what are the forces required. So I want to design a system that the force that required for the assembly these two components is with a force of 3 to 5 Newton. That's system design. Okay. Then subsequently, I go to parameter design. So parameter design, let me back to the slide. So okay, never mind, back to the slide first. So the critical measure for the system design is the force that required, and that force, the force that required to assemble these two components A and B, in fact, is determined by the dimensions of the internal dimensions of part component B and external diameter of the component A. So we call this as a risk. This is the one that perhaps is going to the risk that we might not fulfill the system requirement of 3 Newton to 5 Newton. Okay, so we call this as a risk. And therefore, I repeat, so the system requires us to design something that which is when we assembly, the force is 3 to 5 Newton. So what are the dimensions? That done system design. Next is parameter design. What dimension they're going to control to make sure that I can control the 3 to 5 Newton? I want to control, example, this length. No, this length got nothing to do with the force. Am I to control this length? No, you'd be a bit stupid to control this length because this length also has nothing to do with the force. So what I'm going to do is I will control this diameter and the internal diameter because I know that these two dimensions are the one that are going to influence my parameter, my system design requirement of 3 Newton to 5 Newton. Okay. By saying so, I already completed my parameter design. This not I completed. I already selected my parameter area, which is this. This should be my parameter. Okay, this should be a parameter. So it's a starting. You see, the inner diameters must be bigger than the external diameter of part A. The inner diameter must be bigger than the external diameter of part A. If not, A cannot fit into B. Okay. So now I'm going to do parameter design and tolerance design at the same time. That is the case. No? Normally we do it together. Here is a bit technical. You bear with me. All right. So what I will do, the nominal dimension that I put here is 27 and 27.5. Where you got this? This is the diameter that initial diameter you subject. Okay, so I put it in 27 and 27.5. Okay, all right. So what are the tolerance that you're going to give to these two dimensions? So if you're a designer, you're going to give a tolerance based on the type of material. Okay, we just use example in this case, use a tolerance of plus minus 1 for this dimension and plus 0.05. Okay, where you get this is because I know that this one is made from aluminium. I know. So therefore, the dimension normally is 0.1. And normal upper curve is backed by ABS. So this will be the tolerance. I'm going to show you one of the software that can use to help you to generate this later on. What is bigger gap? Bigger gap will happen when the external diameter here, bigger gap I'm talking about here. What happened to this? Let me check what happened to this first. Okay, so I'm talking about this, bigger gap. The bigger gap of these two components will occur when the diameter of part A is the smallest, and when the inner diameter of, it's not straight, but bear with me, is the biggest. You get me? If B is the biggest and S the smallest, then you have the bigger gap. So when A will be the smallest, A will be smallest at 26.9. And when B will be the biggest, 27.5 plus 0.05. So you get 27.55. You get me? So this is 26.9. And when part A is the smallest, and when part B is the biggest, then you have the bigger gap. And the difference between these two, which is the bigger gap, is the bigger gap. The difference between the maximum dimension of part B minus the minimum dimension of part A, that is the maximum gap. Okay, and smaller gaps will occur when part A here, where's my pen? Okay, part A here, I'm talking about smaller gap. Smaller gap take place when part A is maximum and part B is minimum. So how to get part A maximum? Part A maximum is at the upper spec limit 27 plus 0.1, so it's 27.1. And part B minimum is at the lower spec 27.5 minus 0.05, so it's 27.45. So we got the minimum get 0.35. Okay, there's one thing that I forgot to mention earlier. Specification limit. What is specification limit? You remember that in system design, how I define the 3 Newton to 5 Newton. I make a few prototypes, some model, I test, and then I feel that, oh, 3 Newton to 5 Newton is the force that will be acceptable by customer. And from there, I'll start measure the prototype that I make. And I know that 3 Newtons happens when the gap is 0.05. You get me? And 3 Newton happen when the gap is 0.65. And 5 Newtons, the force required to assembly the component is 5 Newtons when the gap is 0.05. The smaller the gap, the force required higher. So the green color special limit, the dimensions of 0.05, the gap from 0.05 to 0.65 is something that derived from the system design. I recap, system design. Okay, I recap from the initial. You're asked to design component A and B. The first job, this A is going to assembly to B. Okay, the first thing you do is, what are the forces you think that will be accepted by customer to insert A to B? So you do a study, you find that, oh, 3 to 5 is the one that customer will feel happy and will not complain. And from the prototypes that you make, you know that 3 Newtons assembly force occur when the gap between part A and part B is 0.65. And you need 5 Newton force to assembly when the gap is 0.05. Okay, yeah. All right, now, what will be the next? Let me take a look what will be the next. All right, so there's one thing that you can see that system design allow me to have a gap of 0.6, but at this moment, I only utilize 0.3. There's a room for me to play. Okay, next, I will just write down the material, the process, and the part range. Okay, CPK later. So I know that A is aluminum alloy and B is ABS. Someone must remember this. Maybe I need to write down. If not, difficult for me. Okay, yeah, so how to get this 3.29 and 0.05? Okay, you bear me. I'm going to open the software. Okay, this is something that this is a software that commonly used in the industry for robust design with the name of COPRA. Okay, COPRA. Yes, COPRA, correct. So you see, if you refer back to the slide that I showed you earlier, we have component A and component B. Right? Component A, I'm moving here today because I'm watching the background. Okay, component A is make use of aluminium. And the process of, you remember the slide, you have to refer back to the slide. The slide showing that the material is aluminium and the process is core extrusion. So I try to find extrusion here. Yeah, the number of process at the top. So core extrusion. So the dimensions of the component A that we proposed earlier is 27 plus minus 0.05. Is it 0.05? Is it 0.05? Let me confirm again. Oh no, 0.1. You refer back to the slide, huh? 0.1. So if 27 plus minus 0.1, then the predicted CPK is 3.3. Okay, 3.3, yeah? It's 3.3. Okay, this is the first component. Component A, the dimension, the component A is aluminium, and it's produced through an extrusion process called aluminum crow extrusions, and the dimension is 27. The tolerance that we put initially, 0.1. We are doing parameter and tolerance design, and that generates a CPK of 3.3. Okay. Now, back to this slide. So I'm saying that the diameter 27 plus 0.1. I key in, I select aluminium core extrusion. It gives a CPK reading of 3.3. Okay. Now, how about the second process of the component B, diameter 27.5, 0.05, 27.5, 0.05, and it's a injection process, ABS. Okay, injection process. Okay, so instead of extrusion, we try to find injection. They call it plastic mold, plastic molding process, and the material used ABS. Okay, ABS, and then 27.5 and 0.05. 27.5, 0.05. The CPK is 0.05. Okay, 0.05. So you see, here's the one, 0.05. What does it mean? It means that the initial parameter and tolerance that we propose not able to fulfill the CPK of 4.0. Okay, not able to fulfill, we fail to fulfill the tolerance of 4.0. Okay, so how should I do in order to make sure that I'm able to do that? I have to use back the same software. I back to here. I'm not going to change the parameter. I'm going to change the tolerance. Example, if I change the tolerance to 0.1, speaker is only increased to 1.55. How about I change to 0.20? Oh, it's 4. I can keep on trying, 0.18, 3.98. So at the end, I know that I should design the tolerance to 0.2. Okay, 0.2. Because why 0.2? If 0.2, then my CPK is 4. Okay, so I change to 0.2 and I get 4. And by changing that, I need to revise my bigger and smaller gap. Because why? Because the upper limit and the lower limit is no more, it's not the same anymore. The upper limit now is 27.5 plus 0.2 is 27.7, and the lower limit is 27.5 minus 0.2, which is 27.3. If I calculate the gap here, now I got another problem, which is the gap, the bigger gap is bigger than my specification limit, correct? And how to address this? You get me? What is the implication of this? The implication of this is, remember what 0.65? If the gap is 0.65, means the force required to assemble these two components is 3 Newton. If it's 0.8, then how? If 0.8, then I'm going to have the force that less than 3 Newton doesn't meet my system design parameter. So what should I do? Then I back to parameter design. You see, even though in robot design, we're saying that the step is system design, problem design, and tolerance design. But in life, we start with system design, and we try to compensate, I would say, uh, find a trade-off between tolerance and parameter in order to make the specification. So what I can do is, now I can consider changing the parameter here to move the center until the gate is 0.65. So what we'll do is, the range of the capacity, the range of CPK is okay, and then, but the problem is on the gate. So you see, instead of 27.5, the difference between 0.8 and 0.65 is 0.15. So I move the parameter here. You see, I write it here. The difference between here and here is I need to reduce by 0.15. Therefore, I move my parameter. I done my tolerance. I move my parameter to reduce by 0.15. 0.50 minus 0.35 and 0.15 equal to 0.35. And by doing that, my design become robust. I have a CPK that even though this company aims for 4, but if above 3, in fact, it's very good. Above 3, above 2 is very good. 3.29 is great, right? So in terms of CPK, the process is great. In terms of tolerance, in terms of gates, it's meeting the gates. So that is called robust design. And the process is at center. And this is the simple, the easiest example of tolerant stack. When I say tolerant stack means robust design, this is the simplest, the easiest example of robust design. Why I say so? Why I say that that is the easiest and simplest tolerance stack or robust design? Look at this drawing. What is this drawing? This is the robust design drawing. This robust design drawing means a designer is study every single potential risk of the assembly component and identifying what is the CP, CPK, what is the tolerance, and what is the parameter. You see, it's same as what we want, what we discussed. Tolerant design and parameter design. And this tolerant and parameter design have to be carried out on every single component. Therefore, I'm saying that this topic is a bit technical, and the example that I show you, you try to understand, is the easiest and simple example. Okay. Okay, and then that is what all about robust design. I will not give you any tutorial on this. Still, I will let you have the time to look into how to apply robust design in your project task 3. Definitely, you don't need to have the software to calculate CPK. Why? Because you already have the standard deviations from the process. Okay, and that's it for robust design. I'm back with a very tired face. So, as per usual, if you don't understand, you can ask me. Feel free to ask me, especially for this topic. So, what my target for you basically is I just sort of like hope that you can understand the concepts and understand the simple example of robust design that I explained to you earlier. I think this is a good thing of pre-record video. If we conduct this in face-to-face basis, explain once, you don't understand, I have to explain one more time, and perhaps some of you might just skip and didn't raise the problem to me. And the good thing of pre-record video is you can repeat watching the video and you understand. So before I end this video, I just want to remind, and I trust all of you, all the 33 of you. I was sharing the PowerPoint from my ex-company without covering the company logo. So I trust you, and please don't share this with anyone, with any external party, as my ex-company is very particular on that. So we use this for learning purpose, and then hope you keep your promise. All right. That's it for today. A very long discussions on robust design, and see you next round. Bye.